This first one, we are looking at a graph. So through these, we'll look at graphs and calculations related to average atomic mass. On the graph, we're looking at a spectrum. We know that on the x-axis is mass, y-axis, even though it doesn't have values, is the abundance. So we see some tall and some short peaks. The fact that there's two peaks is two sets is really important to come back to this part of the problem, monatomic and diatomic. So hopefully you remember mono is one and di is two, meaning that some of those peaks are from atoms by themselves, and some of those peaks are from atoms bonded to other atoms of the same element. So that's what we're kind of talking about here. The two groups, the mid 30s and the low 70s, relate to the fact that some of them are by themselves, which connects to why these are about twice as heavy. So monatomic and diatomic. And we could sometimes say monoatomic or monatomic. So as we look at the monatomic here, we see that there is a tall peak right at 35 and a shorter peak in the mid-range, probably 37. I know that it's 37. You could argue that it's 36 potentially. And we also see that 35 is way higher than the 37. So those are some good observations there. Even without the other set of peaks, we could use that to draw our conclusion that we've got down here. It's probably chlorine. The next lighter element on the periodic table is sulfur with masses of 32. So we would have to have something in the low 30 range. Argon and potassium come next, and they're in that 39 to 40 range. So we'd have to either have a 40 or something slightly above. So this definitely tells us that it's chlorine. But we can also look at our diatomic peaks. The 70 connects directly back with what we have there, the 35. If I bond a 35 and a 35, I would have a Cl2 or a diatomic chlorine, and it would have a mass of 70. My tall peak here corresponds to a tall peak there. That makes sense, hopefully. Over here, we've got some other ones. We've got a gap and then a peak, a gap and then a peak, but not quite to 75. So that's how we can know that they're probably 72 and 74, which would be made by using our isotopes. The 74, the shortest peak, is made by combining a 37 with 37. That adds up to 74. And rather than needing, for our 72, a 36 with a 36, we know that we could combine a 35 with a 37. So this graph corresponds to figuring out all of these things. When we have individual atoms, we can know that those just correspond to the mass of the atoms. When we have peaks that correspond to maybe something diatomic, that is a combination of our two atoms. They could be two of the same isotope or two different isotopes. We do see some difference here in abundance, taller and shorter, and that is what also connects with the fact that we are closer to 35 in our average than we are to 36 or 37. The other thing that's good to refresh ourselves on over and over is that there's a group of elements, 7 in fact, which are diatomic in their natural states. Sometimes we use different acronyms for them. One that I've always used is the Brinkel-Haas, but it's hydrogen, then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So chlorine right in the middle of that pack, that is almost always diatomic in its natural form. So the fact that we could have a diatomic form of that element makes sense. So when we have our graphs, we have to think, is it atoms or is it a compound? And then how do we interpret that in terms of height, or how could we put things together to make those peaks if it is bonded? When we are doing a calculation, which we did practice in first year chemistry, we normally thought about percentage times the mass, or mass times abundance, till we got our average atomic mass off the periodic table. And that's a very common thing you could still calculate. But if we have masses and abundances and average masses, any of those could be our unknown or our variable. In this case, our copper has two isotopes. An isotope that's just under 63 in terms of its mass, so that'd be copper 63, and almost 79%. Where'd that come from, that 5? I need to clean up my math here, sorry. that 69.17% of it is that isotope. That means the rest of it, and that's where this came from, and man, my math is a mess. Some copying and pasting from an old worksheet will do that for you. But the rest of it is the other isotope. So even though I only have two numbers in this problem, I fill in a whole bunch of stuff. The average atomic mass is from the periodic table. I have my percentage, or my mass and my abundance. But right here, I know that if there's only two isotopes and about 70% is one isotope, about 30% has to be the other isotope. So all of that together allows me to solve for the fact that I know my other one has to be in the 64 to 65 range. And when I do the math here, hopefully we're getting it to come out correctly at around 65. So the two common isotopes, so the two natural isotopes of copper, we would call copper 63. That is copper with 29 protons. That's what all copper has. And then since it's 63, it'd be 34 protons. The other copper has 36 protons. But as I said, those masses aren't going to be exactly the same as the mass numbers. Here, gallium has two isotopes, 69 and 71, and more than just doing the exact math or interpreting a graph, we can also use the periodic table to estimate and interpret. Estimate relative abundances. Well, gallium has an average atomic mass of 69.72. That's pretty close to the middle between 69 and 71, but not exactly. If the average mass came out to exactly 70, we would know exactly that we had a 50-50 mix. So we're slightly, have slightly more of that gallium 69 than the 71. When we're thinking about that in terms of a graph, we would only have two peaks. We're not talking about any compounds. Gallium's not diatomic, so we're just focusing on those two. And then we're showing a graph that's got the one that we just determined to be taller, just a little bit taller than the other one. This looks like it says it's a 60 to 60.11 to 39.89. We wouldn't need to know those exact values there, but slightly taller here than there.